Item response theory. Explain item response theory, RIT. Item response theory, RIT, is an approach used to estimate how much of a latent trait an individual possesses. The theory aims to link individuals' observed performances to the unobservable trait. Because the trait is unobservable, RIT is also referred to as latent trait theory. The literal meaning of latent is hidden. An example of latent trait is a test taker's English reading ability. The construct of reading ability is unobservable or is not observable. So, measuring this ability requires observable performances designed to assess it. For instance, test takers could read a short passage and then answer multiple choice questions designed to measure their comprehension of the passage. RIT can then be used to relate these unobservable performances, scores on the base of multiple choice reading test items, to the test taker's underlying reading abilities. RIT can be used to link observable performance to various types of underlying traits. For instance, it can be used to connect individuals' observed or self-reported anxiety about an assessment to their underlying levels of test anxiety. Now, question is this: explain latent variable. Latent variables are unobservable traits like second language listening ability, which influence observable behavior such as individuals' responses to items on a second language listening assessment. Now, model in RIT. A model is a mathematical equation in which independent variables are combined to optimally predict dependent variable. Now we go to explain parameter. Parameter is used in RIT to indicate a characteristics about a test stimuli. For instance, a one parameter or one PL model mathematically defines only one characteristics of test item, which it is item difficulty and the ability. Now, historical perspectives about RIT. What are two lines of RIT development and what are their differences with each other? Lord and Rach models. Frederick Lord provided the foundation of RIT as a measurement theory by outlining assumptions and providing detailed models. As scholars outline the principles of RIT that they and others had developed in the previous 2 decades. And another kind is by George Rach, a Danish mathematician, is also accredited with developing RIT principles. The primary focus of his research was to use probability to separate test takers' ability and item difficulty. So Rach separated test takers' ability and item difficulty. What about differences? Although the two lines of RIT development have led to quite similar practices, they can be distinguished by at least one major difference. Rach models are prescriptive. If data do not fit the model, the data must be edited or discarded. The other approach derived by Lord's work promotes a descriptive philosophy. Under this view, a model is built that best describes characteristics of the data. If the model does not fit the data, the model is adapted until it can account for the data. While language assessment researchers and practitioners have benefited from both lines of RIT, majority use Rach model. Now we go to critical issues about RIT. First part is to explain conceptualization of RIT. The purpose of RIT is to link test takers' observed performance, such as scores on multiple choice listening tests, to a location on an underlying continuum of the latent traits, such as listening ability. This is made possible by relating the probability of test takers' correct responses to items and the ability of the test taker. RIT assumes an underlying ability continuum with the least amount of ability at the far left and greatest ability at the far right part of it. This is the description about the continuum of RIT. Now, on this scale, the convention average ability is set as 0 and located at the middle of the continuum. Test takers with below average ability have negative estimates, and test takers with above average abilities have positive estimates. In practice, abilities of most test takers can be located between -4, little ability, and +4, variable on the scale. Observable performances aimed at assessing the ability of interest must be used to locate test takers' abilities on this latent continuum. The ordering of test takers' items and resulting patterns of correct and incorrect responses help to demonstrate the theory underlying IRT. Progressing from left to right in the table of RIT, items become more difficult, and progressing from top to bottom, test takers possesses more listening ability. This is explanation of the table and shape of the RIT here, as we have in our article. Now, explain misfits. A practical advantage of probabilistic modeling should be pointed out at these RIT patterns found in data that are highly unlikely to be identifiable. Test takers or items that produce unlikely response patterns are often referred to as misfits. Once identified, misfits can be investigated and decisions can be made about how to handle them. For instance, if a test taker correctly answers most hard items but incorrectly answers most easy items, it may be that the test taker was unfairly distracted during the exam and should be given an opportunity to retake it. Now we come to explain 1PL RASH model or RASH model. This is Danish name. 1PL RASH model, 1PL in RIT, relating test takers' ability to difficulty of items, make it possible to mathematically model the possibility that the test taker will respond correctly to an item. The most fundamental RIT model is RASH model or 1PL. And here we say that for RASH model, relationship between the probability of correct answer, test taker ability, and item difficulty. These 4 items are related to 1PL. Now we go to explain item characteristic curves, ICC. Item characteristic curves, ICC. The relationship between the probability of test taker answering an item correctly and the test taker's ability can also be presented in graphic form in an item characteristics curve, ICC. Then ICC is a graphic form. These graphs can be used to understand RIT principles as well as differences among various RIT models, like 1PL, 2PL, 3PL models. In addition, ICCs are commonly used to help test developers understand how specific items function on an assessment. Being able to interpret ICCs is important for making decisions about which items to maintain, modify, or discard for particular assessment instrument. ICCs present the characteristics of each item at a trace line of probability and ability continuum. The ability of the test takers and difficulty of items are on the same scale. ICCs for 3 PLs, 1PL, 2PL, 3PL, are explained here. Now we go to explain 2PL model. 2PL model. In 2PL, in two parameter models, 2PLs, unlike 1PAs, the shape of ICCs can vary. In 1PL, shape of ICC was the same. Here it can vary. Stated differently, items are not all modeled to discriminate equally. Then item discrimination is added to 2PL model. And while item discrimination was fixed in 1PL. Now, item discrimination refers to the slope of the ICC here. With 1PL, as I said, item discrimination is fixed. All items are assumed to be equally related to ability. But in 2PL, relationship between each item and listening ability can be different. Now we go to 3PL model, the 3-parameter model 3PL, which includes a parameter to control for guessing, is also often encountered in language assessment. When test takers have a significant chance of guessing the correct answer, such as multiple test format, the 3PL may be appropriate. Then in 3PL model, guessing is added, which we didn't have in 1PL and 2PL. In this model, guessing parameter has added to the model. The difference in 1PL, 2PL, 3PL are evident. If we compare their shapes, ICC shapes, they are clear that guessing is added, and 3PL will start with a probability of correct response with chance, which the other ones didn't have it. Now, we go to next part, which it is about summary of them. As I mentioned, 1PL has none of the guessing and item discrimination. 2PL has item discrimination parameter which added. 3PL also we have guessing parameter which we added there. Now we go to next part which will be MFRM and 1PL differences which are not important. We come to current research and contributions to RIT. Let's start with this question. Why do we use RITs? RIT is currently used for various purposes in language testing area. Probably its most commonly reported use in the field over the past 2 decades is for investigating task characteristics and their effects on various types of performance-based assessment. The majority of this research has focused on tasks designed to assess speaking and writing ability. And also, we say that it is used in some large-scale language assessment and is considered one of the most promising applications of RIT here. Let's explain computer adaptive testing, CAT. Computer adaptive tests are designed to deliver assessments that are tailored to the ability level of test takers. The approach capitalizes on the fact that items near the test taker's ability levels are most useful for ability estimation. A computer program to deliver items increasingly closer to test taker's ability level. In simplest form, if test taker answers an item correctly, the RIT-based algorithm assigns test taker a more difficult item. Whereas if test taker answers an item incorrectly, the next item will be easier. The test is complete when a predetermined level of precision of locating the test taker's ability has been achieved. We will achieve the location of the test taker's ability. Explain differential item functioning, DIF. Language testers also use RIT techniques to identify and understand possible differences in the ways functioning for different groups of test takers. Differential item functioning, DIF, which can be an indicator of biased test items, exists if test takers from different groups with equal ability do not have the same chance of answering an item correctly. And then we come to assumptions underlying RIT models. Let's explain the assumptions underlying RIT model. The first assumption relates to dimensionality. Most RIT models require unidimensionality. In a unidimensional data set, a single ability can account for the differences of scores. For example, a second language listening test would need to be constructed so that only listening ability underlies test takers' response to the test items. A violation of this assumption would be the inclusion of the item that measure both target listening ability as well as reading ability, which is not acceptable. Second assumption underlying RIT refers to as local independence. It is that responses to each item on the test are independent of responses to all other items. This means that each item should be assessed independently of all other items. The assumption of local independence could be violated on the reading test when the question or answer options for one item provides information that may be helpful for correcting and answering the items about the same passage. A third assumption underlying RIT, sometimes referred to as certainty of response, is that test takers make an effort to demonstrate the level of ability they possess when they complete the assessment. Test takers must try to answer all questions correctly because the probability of correct response in RIT is directly related to their ability. This assumption is often violated when researchers recruit test takers for a study and there is little or no incentive for the test taker to offer their best efforts. Now, we have sample size in RIT. Let's explain sample size in RIT. Although not generally conceived of as an underlying assumption, a requirement of effective use of RIT is a sufficient sample size. Many factors should be considered when determining the number of cases needed for a sound analysis. In general, a smaller sample provide less accurate parameter estimates. The model with more parameters require larger samples for accurate estimates. High stakes tests require more accurate estimates than low stake tests, and users must decide how much inaccuracy they are willing to tolerate. A minimum of about 100 cases, 100 test takers, is required for most testing contexts when the simplest model 1PL is used. Now, advantages of RIT. First, provided that ability estimates are drawn from the population of interest, they are group independent. This means that ability estimates are not dependent on particular group of test takers. Second, RIT can be used to aid in designing instruments that target specific ability levels based on TIF. Using RIT items or RIT difficulty parameters makes it possible to design items with difficulty levels near the desired cut score. Third, RIT provides information about various aspects of assessment process, including items, raters, test takers, which can be useful for test development. And fourth, test takers do not need to take the same item to be meaningful compared to the construct of interest. Disadvantages of RIT. First, the necessary assumptions underlying RIT may not hold with many language assessment datasets. Second, lack of agreement on an appropriate algorithm to represent RIT-based test scores leads to distrust to RIT techniques. Third, understanding of somewhat technical math which underlie RIT model is intimately too many. As a result, training in the theory and practice of RIT is not always accessible. Fourth, the relatively large sample size required for parameter estimation are not available for many assessment projects. And finally, although RIT software packages continue to become more user-friendly, most have problems with learning it and using it.